Hello and welcome to this Further Maths video for Quarter 1. We're looking at complex numbers, Argan diagrams. So if we look at the notes you've been given here, as well as writing complex numbers in the form 3 plus 4i, we can also plot them on a diagram. And the diagram works like this. The real axis, the x-axis, represents the real numbers, and the y-axis represents the imaginary numbers. So this is very straightforward. Let's just have a look at how we would plot some numbers. So before you start to do this, I recommend that you draw a neat set of axes that cover the whole of the page. You're going to use this page for the next page of the booklet and the page after that. So it's really useful to have a very good diagram. So pause the video now, draw yourself some neat axes, use a ruler, and then restart the video and we'll look at plotting the points. The first point we're going to plot is 1 plus I. So we simply go 1 across and 1 up because the y-axis represents the imaginary numbers. So this is the number 1 plus I, and we usually join the origin up to the point that we've plotted. So that is the point A, which is 1 plus I. Then we're going to plot the point 3 minus 4i. So 3 minus 4i is down here. So this is the point B, 3 minus 4i. And we've joined that up with a straight line to the origin. So it's very much like a vector. Looking at C, we've got minus 5 plus 4i, so that's up here. So we're going to put C minus 5 plus 4i, and we can join it up like that. And then D, minus 2 minus 3i. So there's the point D, which is minus 2 minus 3i. So plotting complex numbers on an Argand diagram is very straightforward. Make sure your diagram is neat and preferably drawn with a ruler. That will help you a great deal. You can see here that we've got one complex number in each of the 4 quadrants. So this is the first quadrant, remember, second quadrant, third quadrant, fourth quadrant. We now move on to looking at what's called the modulus and argument of a complex number. So you can do this referring back to the diagram you've just drawn on the previous page. I've reproduced little mini diagrams here for the purpose of the video. So the modulus of a complex number is just its size. So we're going to use Pythagoras for that. So if I want to work out the modulus of that first complex number, mod 1 plus I, that's going to be 1 squared plus 1 squared square rooted, which is equal to root 2. And that corresponds to the length of the complex number from the origin, if we're thinking in terms of vectors. Now, the argument of a complex number is the angle measured from this real axis in an anti-clockwise direction between the line that represents the complex number and that axis. So if we think about that, we can see that that's 1 and 1. So we can say that if I call that angle alpha, tan of alpha is going to be 1 over 1. So alpha is going to be pi by 4, and they are usually given in radians. So that's A. Now looking at B here, the modulus of 3 minus 4i is 3 squared, is 4 squared square rooted, which is 5. So that length there is 5. So I'm going to write in here that this vector this complex number is 3 minus 4i. Now we've got to find the argument. So I'm looking for this angle here, alpha. And I'm going to say that tan of alpha is equal to, so this was 3 minus 4i, so it's 4 over 3. Tan of alpha is 4 over 3, and that gives me that alpha is 0.927, but the argument of this vector of 3 minus 4i is minus 0.927. And the reason for that is that we measure angles in an anti-clockwise way from the real axis. So this is then clockwise, so that's why it's negative. And if you always draw a diagram for your complex numbers, even if it's just a little diagram like this, you can quickly see whether you're going to need a positive or a negative angle. For C, we are looking at minus 5 plus 4i. So that's this point here. So that is minus 5, and that distance there is 4. This distance here is 4. So if we want to find the modulus of this vector, that's going to be the modulus of minus 5 plus 4i is equal to 5 squared plus 4 squared square rooted, and that is equal to the square root of 41. Now we need to be careful here. We want to find that angle to start with, and then we're going to subtract that from pi. So we're going to say inverse tan of 4/5, and that's equal to 0.675. I would use my calculator for that. I've actually calculated that already for the purposes of this video. We then need to work out pi minus 0.675, which is equal to 2.47, because we want this angle here. 180 degrees is pi radians, so we need to take away the angle that we already got for this little bit here. So the argument of this complex number here is equal to 2.47. Let's look at the last example. We've got minus 2 minus 3i. So that distance there is 2 minus 2, and that distance there is minus 3. And again, we need to say that the modulus of minus 2 minus 3i is 2 squared plus 3 squared square rooted, which is root 13. And then we want the argument. So we need to find, first of all, this angle here. So we're going to say inverse tan of 3 over 2. And that is equal to 0.983. Then I want to say pi minus 0.983, because I want this angle here. And that gives me 2.16. But the overall argument is negative. So the argument of minus 2 minus 3i is equal to minus 2.16. And that's the argument of that vector. Notice that we choose to give the argument between minus pi and pi radians. So if we draw the real axis there and the imaginary axis up in that direction, we are saying we're going to go from 0 to pi and 0 to minus pi. That really is just a convention. You might find some textbooks or your university course when you go to university takes this to be 2 pi, 0 to 2 pi. Which is another convention you can use. And it doesn't really matter what convention you use, so long as you're clear on what you're doing. So in this course, we will generally be taking the argument to be between minus pi radians and pi radians.